Hey guys, welcome back, and today we're going to be going over counting with atoms, otherwise coined as atomic accounting. Now, this skill is really important when it comes to learning the basics of chemistry and the interaction between elements and atoms to be able to form compounds. So it may seem a little bit easy to some of you or really redundant, but I promise it'll come into important use in the future. So, to start off with this, we have to review the subatomic particles and understand the basics behind the atom. So, what I have drawn here is an atom for you, and we have our nucleus right here, the very center. And in the nucleus, we have two different kinds of particles, as remember. So, we're going to have our neutrons as one of them, and then we're also going to have protons. Now, for the sake of time later and writing things out, I'm gonna give these guys labels. So neutrons are N with a small zero, protons are P with a small plus, so on. The last particle that is not part of the nucleus is the electron. So I've got these tiny dots drawn in a larger area of space around the nucleus, and that's to show that electrons have a unique particle wave duality that you'll learn about later. But we present them as particles simply for understanding at a very basic level. But later on, you're going to learn that it's not so simple as electrons looking at like points in space. And also here, I'm going to label these as E with a small negative. Now, overall, we know that each of these has its own unique charge as well. So neutrons, as indicated by this small n sub zero that we have, they are neutrally charged. Protons are positively charged. And to complement this, electrons are negatively charged. Now, in a neutral atom, emphasis on neutral, the number of protons equals the number of electrons. And I'm going to emphasize this over and over and over again so that you understand that an atom has to be neutral in order for this to be true. So this brings us into how do we talk about these terms in relation to everything else? We're not just going to be randomly asking, oh yeah, what's the number of neutrons in this? We're usually going to be asking about a different number initially. So two of the most important numbers you're going to need are the atomic number and the mass number. So initially, the atomic number is the number of protons in the nucleus. And it is usually written right here in our notation. On the contrary, when we're talking about a mass number, this is actually the mass of protons and neutrons in the nucleus. Now, it's important that we remember this well because we denote these numbers differently when we're writing out the notation for an element. This is also going to play a bigger effect later because if we know the atomic number and we know the number of protons in the nucleus, this can it can tell us about the number of electrons, and we can also figure out the number of neutrons. Using both this and the atomic number. And this will make sense in a little bit when I go over what this essentially means. Another important distinction to make, not just about the atomic number being the number of protons, positively charged particles in the nucleus of the atom, is the fact that we talk about the mass number. So the mass number is always a whole number. Sitting here, if you were to look into your lab notebook, you would know that on the periodic table you have bolded numbers, which are your atomic number. It tells you the number of protons, and this is actually how the elements are arranged on the periodic table. As we move from left to right, we increase our number of protons by 1, and it goes on like this. And this actually enables us to align the elements according to similar chemical properties and physical properties in the periodic table. Mass numbers are not on the periodic table. And don't get this confused with the numbers on there that have decimals. Those numbers are not mass numbers. Those are average atomic mass numbers. We don't care about those right now. We only care about this one. And the mass number is reflective of this, of the number of protons and the number of neutrons, and the number of neutrons can vary. This is why the mass number is always a whole number. It's not a decimal, because that average atomic mass is reflective of the average of all of the different masses of an atom of the same element that exists in nature. And this has a very specific name. These are called isotopes. Ignore that spelling. Isotopes. And we'll come back to a little bit more on that in a little bit. So we know, why do atomic number and the mass number matter? Well, going on into the future, we know that the atomic number equals the number of protons and the number of electrons in a neutral atom. And then the mass number equals the number of protons plus the number of neutrons. We know that this is always a whole number, because this can vary, which leads me into the next slide. Fun facts about isotopes. So the official definition of an isotope is that it is atoms with the same number of protons but different numbers of electrons. Not electrons. Neutrons, guys. Neutrons. Pardon that. Atoms with the same number of protons but different numbers of neutrons. It's the only thing that changes. And this can do that because as long as our protons and our electrons balance out, we can have atoms that have different chemical properties going on. They can bond with different other atoms. They can create different compounds. The neutrons really don't play a part in that, as in the fact that they contribute mass to the nucleus, and they actually contribute stability to the nucleus. So why do we care that isotopes exist, besides the fact that it makes doing calculations with average atomic mass or a mass number a little bit complicated, because we have to remember the distinction? Well, isotopes are actually used for carbon dating. They're also used to track nitrogen bases in DNA. And a thought that just comes most to mind right now is they're also used in nuclear energy. And all of these are examples of radioactive or unstable isotopes. Sorry about the lines, don't know why those happened. But for instance, nuclear energy, we actually relied upon a very specific isotope of the element uranium when we were creating the very first nuclear bombs and creating nuclear power plants. We relied upon something called uranium 235, which means its mass number is 235. This means that it also had an unstable number of neutrons in its nucleus, which enabled us to carry out a process called fission. And if you're interested in more about this, you can look it up on the internet and read about it and see what it actually does. It's pretty interesting, and it produces a lot of energy, and it's a pretty catastrophic reaction when it goes uncontrolled. But either way, you want to know why isotopes matter? This is why. So now to get into a little bit more of the boring stuff, we have to talk about the notation that's going on. So as a review, the protons plus the number of neutrons equals the mass number, and the number of protons equals the atomic number. And here, the atomic number is always labeled on the bottom left, and the mass number is always on the upper left. And this right here is our element symbol. So some examples of this, when you look at the periodic table, it's not the full name. Examples would be like C for carbon, N for nitrogen, Zn for zinc, Mg for magnesium, so on and so forth. Now, you don't always have to write the designations for elements in this way. You can actually write them as an element name with a mass number. I showed an example of this in the previous slide. So an example, just simplistically for you guys, would be carbon 12. We have our element name written with a hyphen, and then we put the mass number. And from there, we can usually figure out all of the other stuff that we need to know, because if you know the mass number and you know the element name, you can track it down on the periodic table and find what its atomic number is. The nice thing about the elements in the periodic table being organized the way they are. So let's do examples of atomic counting. Now, disclaimer going into this, these things do not always look this nice, because first off, the number of electrons is not always equal to the number of protons. It simply just does not always happen. It usually isn't like that in nature. Another thing is that not all elements are going to have equal numbers of neutrons and protons within their nucleus. It's just the way that things work out. It works that way a lot of the time, but not always. All right, so starting off, we have oxygen, and we're given a mass number of 16 and 8 neutrons. So to start off, our atomic number equals our number of protons, and our number of protons plus our number of neutrons equals the mass number. So 16 minus 8, as in the mass number minus number of neutrons, would equal 8. So our atomic number is 8, and if you look at the periodic table, oxygen does in fact have the atomic number of 8. And because the atomic number is 8, we know that the number of protons is also 8. And because this is a neutral atom, the number of electrons has to equal the number of protons. So it is also going to be 8. Now, next we have nitrogen 14. We're given the atomic number, but in the name, we are also given the mass number. So we have 14 here. Our number of protons is the atomic number, so that's 7. Our number of electrons equals the number of protons, which is also 7, because this is a neutral atom. And then the mass number minus the number of protons equals the number of neutrons. So 14 minus 7 is 7. Next, we have sulfur. We're given our number of electrons, and we're given our mass number by the notation. So we can write the mass number down, which is 32. The number of electrons is 16, which means we don't need to do any math. We know that there are automatically 16 protons, and this has to match the atomic number. And 32 as the mass number minus 16, the number of protons, equals 16, which is our number of neutrons here. All right, last is lithium-6. So we're given the number of protons. We're given our mass number, which is 6. So we know that the protons equals the atomic number, so that's also 3. The number of electrons equals the number of protons, because it's a neutral atom, and so that also equals 3. And then our mass number minus the number of protons equals 3 yet again. It's pretty simple going into it like this. Now, protons and neutrons are pretty important. They make up literally like 99.9% of the mass of an atom, which is odd because they don't make up all of the space that an atom sits in. But Now we're going to talk about the real interesting part of the atom, which is actually the electrons. People have been studying electrons for decades, as can be seen, because they were discovered in 1897 by J.J. Thomson, yet we still don't know some things about them. We still can't prove some things about them. In fact, they still confuse us because they're pretty complicated. Now, we know that the charge is equal to a proton, and as I just said, but their mass is not equal. Don't confuse this. While the charge is equal, the mass is much, much less. We're talking like if a proton and a neutron have a mass of around 1, an electron has a mass of like nothing. It's approximating 0. That's exactly how much mass it has. So we have a hard time. We can't measure a change in mass by removing or adding electrons directly. We have to do it with indirect methods because they simply don't contribute enough mass for it to matter ultimately. Now, you're going to ask, how do we determine the number of electrons? Well, it's easy. In a neutral atom, it's the number of protons equals the number of electrons. Haha, yes, that works. Except when we don't have a neutral atom. And most atoms that are in nature aren't always neutral. They are charged, or they have given away some of their electrons, or they've taken some more on, which means, yeah, we're going to have to figure that out. So normally, we're going to be given a designation. We're going to be told that this atom is charged and that it has either lost or gained electrons. And so to figure out what had the number of electrons it has, we're going to take the atomic number and we're going to subtract the charge number. And this will make sense once I show you why this works. So we have a definition for these atoms that are charged, and they're called ions. They are elements with different charge numbers but the same atomic number, hence why they are part of the same element, and they are called ions. So all about ions. Ions are formed with the gain or the loss of electrons, and this is always with the gain or loss of electrons because protons are in the nucleus and they're bound to neutrons, and there's like this tightly compact ball. We don't lose protons. We don't lose them like ever unless you are undergoing some crazy nuclear energy reaction where fission is occurring. You see, it doesn't happen. So it's only electrons that we're dealing in here. And simplistically put, atoms that lose electrons become positive. Atoms that gain electrons are negative. This makes sense because electrons are negatively charged. If we take a negative charge away from something, then it's going to have more protons overall and therefore have an overall charge that's positive. When we add electrons on, we're going to have more electrons than protons, and because the charges can be set equivalently, we're going to know that it's going to have an overall negative charge because there's more electrons. Now, this is usually written like this, where we're going to have the element symbol, as always, our atomic number, and then our mass number. And right here is the charge number. So it's that tiny z that we talked about in the last one. And it's always written like this, where you have the number and then the charge is 2 minus. And then in the case of lithium over here, it is plus or 1 plus. The 1 goes without saying. We don't need to write it. It's implied. We know that when we put a single plus or a single minus, it's just 1. Now, this is where this gets a little interesting. We did atomic accounting, literally, before, where we had to figure out the number of protons, electrons, neutrons, atomic number, and the mass number from a neutral atom. Now we're doing this with a charged atom. So the atoms that I have listed here are different than the ones that are in your notebook. You can try those ones on your own. Here's some that we can do together, or at least I can do for you to kind of show you what this looks like. So starting off, we have zinc. Both the mass number and the atomic number are given to us. So we can write 64 in for the mass number, 30 for the atomic number. Now, we are also given its charge. It's plus 2. So going by that formula that we have, where it's the atomic number minus the charge number, we can actually write this as 30 minus 2 equals 28. So the number of electrons is 28. So we know that. We know that the atomic number equals the number of protons. So we have 30 of those. The mass number is 64. 64 minus 30 gives us 34 neutrons. Moving on. Now we have lithium plus. So we know the atomic number and the mass number yet again. So we put a 7 in mass number, a 3 for the atomic number, and we have 3 protons. Going by this again, we're going to take our atomic number, subtract off the charge number, and this gives us 2. So we have 2 electrons, and we do the mass number minus the atomic number, 7 minus 3. This gives us 4 neutrons. Now we have F minus. We know the mass number and the atomic number again, so it's 19 and 9. We know our number of protons, which is 9. And from here, we figure out the number of neutrons. So we have 19 minus 9 is 10. Now for the electrons, this is where we have to be cognizant of sign. So we have 9 protons, or 9 for an atomic number, and we want to subtract off the charge number. But the charge number is negative. So it is 9 minus 1, which actually is 9 plus a positive 1. So we have 10 electrons, which makes sense. Before this, we were talking about positively charged atoms. And as we remember from before, atoms that lose electrons become positive because they have more protons overall. They have a greater positive charge. Atoms that gain electrons become negative. They have an overall negative charge because they have more electrons than protons now. So this is true of here. In zinc 2 plus and in lithium plus, we're going to have a smaller number of electrons comparative to our number of protons because they are positively charged. We have lost electrons. With fluorine, though, we have gained an electron, and so that we have to be aware that logically, yes, we're just plugging this into a formula, but this is how this is going to work. Just we need to make sure that our answers always make sense. And I just realized I wrote this wrong up here. This should be 2 plus. Pardon me, guys. Anyways, to keep going, now we have aluminum 3 plus. And we're given the atomic number and the mass number again. So we write 13 and 27. Our number of protons is 13. Our number of neutrons is 27 minus 13, which is 14. And our number of electrons is 13 minus 3, which equals 10. So we have 10 electrons. And then finally, we have nitrogen 3 minus. So we are given the mass number and the atomic number. So we're going to write a 7 into here and a 14 into here. We have 7 protons because the atomic number is 7. 14 minus 7 is 7 for 7 neutrons. And then we're going to have 7 minus a minus 3, which equals 10 electrons because 7 plus a positive 3. So that is how we do that for an overall look at how neutral atoms and ions play together and how we're going to figure out the number of electrons to be able to designate a charge or to show what a designated charge means to us in terms of electron density and how that compares to the number of protons and the number of neutrons. If you guys have any questions, ask Miss Miriam. If you need any clarification, ask her. I hope this was interesting, and good luck working on all of your worksheets coming up.